Welcome, listeners, to People Behind the Science. I'm Dr. Marie McNeely, your host for the program, and I am thrilled to have you joining me today for episode 432 with Dr. Ellen Zweibel. Now, listeners, if you love the People Behind the Science podcast and you want to help us on our mission to share stories from scientists to inspire people and make science interesting and accessible to everyone, we would love to have your support in our Patreon crowdfunding campaign. Please visit us at patreon.com/sciencepodcast to learn more. Now, in today's episode, Ellen is going to chat with us about her experiences in life and science. So get ready to meet another one of our exceptional people behind the science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of the People Behind the Science podcast. Listeners, today I am thrilled to introduce you all to Dr. Ellen Zweibel. So, Ellen, thank you so much for joining us on the program. How are you?
I'm good. How are you?
Wonderful. We are excited to have you today and excited to learn more about you and your work. And I want to start by telling our listeners just a little bit about your background. So listeners, Ellen is the W.L. Kroshar Professor of Astronomy and Physics and the Vilas Distinguished Achievement Professor at the University of Wisconsin-Madison. She received her bachelor's degree in mathematics from the University of Chicago and her PhD in astrophysical sciences from Princeton University. Ellen then served as a faculty member at the University of Colorado for over 20 years before joining the faculty there at the University of Wisconsin in 2003. Now, Ellen has received numerous awards and honors during her career, including being elected as a Fellow of the American Physical Society and being awarded the American Physical Society's Maxwell Prize for Plasma Physics. And listeners, Ellen is here to share more about her experiences in life and science today. So Ellen, we want to get to know you both scientifically and personally. So can you start by telling us how you spend your time when you're not doing research?
So all my life, I've done some art and I've done some creative writing. I've kept a journal since about 1977.
Oh, wow.
But I actually spend a lot of time on my research, my teaching, working with graduate students, and I don't have all that much juice left to do those things right now, although at some point I will get back to them. So my main activity now, which I try to be very regular about, is running. I run every day. I run for at least 45 minutes. And on my birthday, I run my age in years in minutes.
Oh, wow.
Which someday I won't be able to do that.
I was going to say, it's going to get increasingly hard.
But right now, it's a great way to reflect on my life. And my birthday's in December, so sometimes there's snow. Sometimes it's more like hopping and sliding my age, but I do that.
That is awesome. I love that tradition. I'm going to have to adopt it myself. Now, you mentioned you dabble in art as well. Can you tell us a little bit more about what kind of art you like?
Well, my own art right now is just sketching. So I keep my journal with me when I travel. I sketch. It's a great way to really see all kinds of details when you're sketching that, well, I at least would not notice, and that I certainly wouldn't notice if I were just taking pictures. So I love to draw. I have paints, watercolors, acrylics. I haven't set up in oils for a while because you really have to dedicate space to that. I've done some clay sculpture, but nothing with a chisel, nothing with a saw. Mm-hmm. And my favorite kind of art is painting from the Impressionist period. That's what most resonates with me.
That's awesome. And I'm quite impressed that you mentioned you kept this journal since the 1970s. Has this been sort of a continuous effort? Are there gaps in the timeline?
No real gaps. It's just been good. It's like having someone to talk to. It's an opportunity to reflect on the day. I don't usually write a huge entry, but it's a good way to keep in touch with myself and sometimes go back and read my old entries and see what I was obsessed with at some particular time.
I was going to say, I'd be curious to go back in my memories and look back, but like, what was Marie of 20 years ago interested in? You know? That's awesome. So now we'd love to talk about your science as well on this program. So Ellen, can you tell us how you describe your work to someone who's not familiar with plasma physics and what you do?
So I study electricity and magnetism in the cosmos. And I guess I'd like to stress that when I entered astronomy, I was not one of those people who fooled around with electrical equipment. In fifth grade, we made an electromagnet, but I wasn't one of those people who was always hooking things up. Electricity and magnetism in the universe is very, very different. If you think maybe about a system like the ocean, so the ocean is full of waves and currents and ripples. And if the ocean were a plasma, meaning that it had free charges in it and a magnetic field in it, it would behave in an even richer and more complicated way. So the kinds of things I study are the existence of sunspots, the existence of the solar cycle, and high energy electromagnetic emission from stars and galaxies, X-rays, gamma rays, radio waves. That's all kind of the bread and butter of plasma astrophysics.
Excellent. Well, I look forward to chatting more about some of your current projects as we go through our conversation today, Ellen. But I'd like to hear a little bit about what motivates you. I think, like you said, it's hard to find free time as a scientist. You've got a lot going on. What are some of the things that keep you going in every day, or the quotes or sayings that you really resonate with?
So the kind of research that I do, it's sometimes called curiosity-driven research. So I'm not trying to make a better flavor of Tang or invent something. It's pretty abstract. What drives me is curiosity. And I think people have always wanted to know what the world is made of. And our understanding of that is more sophisticated now than it was. We understand that the universe is ruled by laws, probably a fairly minimal set of physical laws that give rise to this incredible richness of phenomena that we all know and experience every day. I've never found a research problem that didn't get more interesting as go into it. Sometimes you think something is going to be interesting. It turns out not to be so interesting.
Right. Great disappointments. Yeah.
Yeah. It never happens with research. It's just always more subtle and more surprising than you expected it to be. One of my students came to me the other day and he said, I have bad news. I made a mistake in my computer program and I have to rerun a bunch of models. He's modeling something in a galaxy. Mm-hmm. And I said, that's not bad news. It's good news. Because when you get the new results, they'll make more sense and they'll be more interesting than your old results. And I didn't just say that to make him feel better.
Sure.
It's really true. When you really understand how something works, that's just the most exciting feeling.
Absolutely. Well, I love that you have that twinge of optimism too. So do you consider yourself a pretty optimistic person?
Well, I'm not optimistic about everything. For example, I'm not very optimistic that we're going to respond to climate change in an appropriate way.
Sure.
But I do think that the way the universe works is probably the best way it could possibly work.
Sure. So, Ellen, do you have a favorite motivational quote or saying that you like to tell your students when they come into office with bad news?
No, I can't say I have a single quote, but there's a pretty universal set of fears that I went through myself. Students doing research are always afraid that somebody's going to do the research that they were doing faster or first. That's practically never the case. People can be working on similar things and everybody kind of finds their own way in, their own approach, their own sliver of the truth. So I try to calm them down. And I think that a lot of being a student is finding your voice. And some of them are going to find their voice in science, doing what I do. And some of them are going to find their voice doing something else. It might be completely different. It might have nothing to do with science. But that's part of being a human being, is finding your authentic voice, your best expression of your best self. And I try to help my students do that.
Absolutely. Now, when you think back on your own career, Ellen, were there specific people who maybe motivated you to pursue science or helped you find your own voice?
Yeah. So my father was a machinist. He had a deep love of science, popular science. And so he explained a lot of things to me when I was a little kid, and I kind of took to them. I had a wonderful science teacher in sixth grade. He didn't follow any kind of curriculum. I think he drove some people crazy, but he told us fascinating things and he had us doing interesting things like balancing nuclear reactions. I just found that so exciting. I had teachers who were more interesting, less interesting. The same was true in college. I was very lucky to be able to do research from the time I was a freshman with a professor at the University of Chicago. I did research with two professors when I was an undergraduate. I did have some wonderful teachers, probably too many to name. So, yeah, they were very important.
Absolutely. So when you think back, I mean, you mentioned that your father was a machinist and maybe helped cater to your curiosity. Do you have a memory that was maybe one of your earlier instances of getting interested in science and wondering how the world works?
Yes, I have two. So when I was very little, 3 or maybe even 2, he was talking to me about why people get sick. And he told me about bacteria and viruses and painted this exciting picture of these one-celled organisms. And I wanted to see them. Mm-hmm. And he said, we can't see them. They're too small to see. And I was so disappointed that I went to sleep, and I remember a dream in which I was standing on the threshold of a room that was full of these illuminated fish tanks. And they were full of these little creatures. But of course, I didn't know what they really looked like. So I woke up before I could enter the room and see these creatures. Mm-hmm. That was very exciting. And then years later, so my father collected science fiction, and our attic was full of science fiction magazines going back to the 1940s.
Oh, wow.
And these magazines had a regular science column. And I would go up to our attic and just sit. The attic wasn't finished, so I would just sit on these boards and just read these columns. And there was a column from a 1950s issue about how the planet Jupiter had passed in front of a star. That's called an occultation. And as the star sort of slid behind Jupiter, Jupiter's atmosphere absorbed some of the light, and that enabled scientists to see for the first time that the atmosphere of Jupiter contains methane and ammonia. So this had not been known. So there were two things about that really struck me. So one was this idea that every molecule, every element has a chemical fingerprint. It's called a spectrum. And I really love that. But what was even more amazing to me was that astronomers were able to predict that one tiny pinpoint of light was going to pass behind another tiny pinpoint of light, that you could chart the motion of objects with such precision. I had no idea that that was possible. And that was even more exciting to me. And I guess that was the first clear demonstration I had of the regularity of the universe and the strength of physical laws that I alluded to a few minutes ago. That was really exciting.
Absolutely. I think these things are still remarkable to me when I think about them. I love this memory that you've shared with us, this picture that you painted of a young Ellen reading through these old magazines in a dusty attic and just having your mind blown by the wonders of science. So can you tell us a little bit next about, you mentioned this experience that you were able to get in undergraduate working in a research lab. What was it like the first times that you got that exposure?
Well, University of Chicago was a wonderful place for me to go to college. I hadn't finished high school. It was really a struggle, but it was like a small college embedded in a great university. So orientation week, I went around and I talked to 2 professors about whether I could do work with them. I got 2 job offers. And one of them was a guy who detected cosmic rays, which is actually what I study now. And I'll be talking about that later, I guess. But his students, he had me talk to his graduate students, and they went up to Hudson's Bay. They flew these high altitude balloons, and they went driving around on the tundra, recovering these balloons. And I thought, I can't do that. I can't even try. So that was not for me. And the other one was a young radio astronomer named Patrick Palmer. And he had also been an undergraduate at Chicago. And I think he kind of wanted to give something back. He had worked in a chemistry lab, I think, and he liked the idea of having an undergraduate student and being their mentor. So I started working with him. And in those days, you didn't do computing just sitting at your desk, pecking away on a laptop or a desktop. You actually punched cards, IBM cards, and you took them to a computer center, and they would run their cards through the card reader and the output would come out. Mm-hmm. So he gave me this big deck of cards to run a program. And I went over to the computer center and I stood there, and all kinds of important people came and went getting their programs run. And I was just too shy. I just stood there for a long time, too shy to ask the operator to run my cards.
Oh, no.
But finally, he noticed me. And he said he was going on break and would I like to go out with him for a hamburger? So I said, okay, but could you please run these cards? So he ran the cards. We went out for a hamburger. He later became a friend. So in the beginning, doing anything was a struggle for me. But I got my legs eventually and began to understand more and more things, did little problems by myself. The other professor I worked with was named Peter Vandervoort. We wrote a paper together on the mass and the disk of our galaxy. It was really exciting.
Well, that sounds like a wonderful experience. And I think a lot of our listeners out there can probably commiserate with this experience of just sort of feeling a little bit like a fish out of water that first time that you're thrust into a new environment and trying to do something different. So I think it's reassuring to hear that you can go on and become a successful scientist, even though you've had these awkward early moments.
Well, they were awkward. And I keep reminding myself when I'm starting off a new student, if they don't make much progress in the beginning, not to be too disappointed and sort of remember what things were like for me. They didn't give up on me.
Yeah. And you mentioned you had some struggles, particularly towards the end of high school. Can you tell us a little bit about what happened then and how that affected your decisions then for college?
The struggle was that I wanted to go to college. That wasn't really a struggle.
Mm-hmm.
So I went to the National Science Foundation used to have, I don't think they do anymore, have these programs for high school students where you would go to a university for 6 or 8 weeks and there were special classes for you and maybe a lab experience. We lived in New Jersey, and I went to one in mathematics at Utah State University out in Utah. And the whole thing was such an amazing experience. I'd never been west of New York. So to take a bus to Utah, it was just amazing. And then there were I had never met kids who lived in any part of the country except the East Coast. Everyone was so different. People dressed differently, talked differently. And I loved living in the dorm and taking these courses, these math classes. There were 2 math classes for us. And when I came back, I was, I guess, pretty impatient to not be in high school anymore.
Gotcha.
This was before my junior year of high school. Mm-hmm. And my mother found the University of Chicago for me. The University of Chicago has always had a policy of taking people who haven't finished high school, taking them a little early. And I was fortunate enough to be accepted, and it was great.
Oh, that sounds like a wonderful experience then. You were ready and raring to go. So,
well, I wasn't so ready. When I came, I had many people take calculus their senior year of high school. Mm-hmm. If I had stayed in high school, I would have taken calculus. I didn't really know there was any math beyond calculus. I thought it was
sort of the end,
sort of the epitome of higher mathematics.
Yeah.
When I got to college, and it just seemed I was surrounded by people who knew calculus, and I didn't know any myself, and I just thought I would never catch up. It was actually pretty daunting.
Sure. Well, we've talked a little bit about your scientific journey, and I know you are doing amazing research there now. So do you have a favorite project, Ellen, that you'd like to tell us about in a little bit more detail today?
So most of my time now is spent studying cosmic rays. And cosmic rays were first discovered to be cosmic in 1912. So can I tell you a little bit about how they were discovered?
Yeah, that'd be great.
So it was known even in the 18th century that there's some free electric charge in the air. And no one really knew where this came from, but people thought it most likely came from underground. And when radioactivity was discovered, it was assumed that radioactive elements in the earth were the source of this ionizing radiation. And there was an alternative idea, which was that the ionizing radiation came from space. And someone actually went up the Eiffel Tower, which was, I think, the tallest building at that time, and said, well, if we get more ionization at the top of the Eiffel Tower, then it probably comes from outer space. But he didn't get any result. And it turns out the Eiffel Tower is not high enough. So in 1912, an Austrian physicist named Victor Hess went up in a balloon. He went 5 kilometers up. And he showed that the charge in the atmosphere increases with height. So he said this must be coming from outer space. And they called this ionizing radiation cosmic rays. And we now know that cosmic rays are created throughout the galaxy. And let me give you an analogy. Our galaxy is filled with tenuous gas, the gas between the stars. It's called the interstellar gas. And about 1 interstellar atom in a billion is a cosmic ray. So, Marie, what is the temperature? Are you sitting inside? Are you sitting somewhere?
I am inside, a cozy 70 degrees.
70 degrees. Okay. So imagine if the room you're sitting in were like the interstellar gas in our galaxy, the temperature would drop by 1/2. You would suddenly be sitting in a 35-degree room, but one particle in a billion would have so much energy that it would be lethal. If it hit you, it would do radiation damage.
Oh, wow. This has become stressful, Ellen. No.
Well, I'm not trying to cause stress. I'm trying to show you how surprising this is.
Yeah.
So we know that this will never happen in the rooms we sit in. According to the laws of probability, it could happen, but it's incredibly unlikely to happen. It never happens. But in interstellar space, it has happened. And we think what is causing this extreme energy inequality in the interstellar medium, where one particle in a billion has half the energy of all the other 1 billion minus one particles, is the magnetic field of the galaxy interacting with exploding stars, supernovae.
Cool.
We think this is what happens. So what I study is that 1 billionth of particles and how they interact with the magnetic field and with the rest of the gas. And we think they can do all kinds of things. They can drive gas out of galaxies. They can heat the gas, accelerate it to high velocities. I study all this together with students.
Very cool. So in talking about this particle, you mentioned that they're quite rare, 1 out of a billion. How do you find that 1 out of a billion particle?
A billion sounds like a lot, but actually, if you could count all the atoms in 1 cubic centimeter of the air you're breathing, it would be about a billion billion. So
1 out of a billion is not bad, right?
It's not so many. So the way we originally found them is that they come to Earth and they're detectable in cloud chambers. So if you have a sealed chamber and you just increase the pressure so that it's about to condense into water, but hasn't quite done so, and then you put high energy particles through it, they will leave a little trail. That's sort of the oldest technique for detecting subatomic particles in cloud chambers filled with vapor or maybe dry ice. You can do it with dry ice too. So that's how they were first discovered. And that's still how some of them are discovered. And the very highest energy ones, so the highest energy particles, just one little proton nucleus, one little hydrogen atom, has as much energy as a well-hit tennis ball.
Wow.
So Venus Williams, kind of best served, will be like one of those particles. Much higher energy than we can make in accelerators on Earth, like the Large Hadron Collider. Now, these particles, when they enter the Earth's atmosphere, they break up into showers. And those showers spread over many kilometers. So we have detectors spread out over many kilometers. There's one called the Auger detector in Argentina, one in New Mexico, I think one in Utah. So that's how we see the ones that come to Earth. But we can actually see them all over the universe because as the high energy electrons move in the magnetic field of a galaxy or an intergalactic space, they emit a kind of radiation called synchrotron radiation. So we can observe synchrotron radiation. It mostly comes out at radio wavelengths. And when the cosmic ray protons and atomic nuclei collide with interstellar particles, they produce a type of subatomic particle called a pi meson. They produce lots of pi mesons. And some of those pi mesons decay into gamma rays, very high energy light. And we can see the gamma rays now. That's been a great innovation in the last couple decades, being able to see these gamma rays. That's how we see them.
Excellent. So now, is there one particular burning question that you're working on right now related to these cosmic rays?
So cosmic rays are called cosmic rays because when they were first discovered, nobody knew if they were charged particles or light, high energy light or high energy particles. And that wasn't established for about another decade and a half. So the name has stuck, cosmic ray. So I'm going back and thinking about the difference between how cosmic rays and light act in the galaxy. And there are some similarities, but there are also some differences that mostly have to do with the fact that cosmic rays respond to the magnetic field of the galaxy and ordinary light does not. So together with my students, we're kind of really digging in and trying to explore the consequences of that.
Very cool. Well, Ellen, in hearing about your research, I love that you've kind of interwoven the history of the field within your description here. That's very cool. And we've touched on some of the different challenges that you've encountered over the course of your career and that you're sort of dealing with now in the field of research that you work in. But I really like talking about these challenges and highlighting some of the challenges and failures that scientists face, because I think they don't always make it out there in the media. So do you have a favorite story of failure or challenge that you want to share with us today?
There have been enough small failures that if you took all the paper that I've recycled over the course of my career, you could probably grow a small forest.
Oh, wow.
Most of the things that I try to do, most of the ideas, they're not that sound on further examination. So my recycling bin kind of fills up. So you asked if there was anything funny, and I don't know what would be funny. Maybe to your listeners, maybe the whole thing is funny. that someone could care so much about this stuff, but I do. So I'll tell you things that are never funny. No question is funny. No question is stupid. Usually people have a reason for thinking the things they think, and it's always worth paying attention to, even if it's wrong.
I love that you mentioned that a lot of the ideas, I think it's important to just get them all down on paper and examine all of your ideas, because you never know which one is going to, upon further examination, turn out not to be a good idea, and which one, upon further examination, is actually going to be more brilliant than you even realized. So
one I think of when I wake up at 2:00 in the morning is usually not any good.
Right.
But the ones I think of when I'm running, actually, that's a better track record.
Oh, excellent. So now you know how to cultivate the good ideas. You just got to keep on running.
As long as my legs can hold up.
That's right.
Work I do on airplanes is often wrong.
Yeah, airplanes are not a good place to get work done. I've given up. I just read on airplanes now.
Yeah, you see people working. I don't know how they do it. Most of what I do on airplanes is wrong.
Yeah. So we've talked about the challenges, but we don't just want to talk about the difficult times. Ellen, is there a success story that you want to share with us today, whether it was a big one or just maybe a recent small one that meant a lot to you?
Yeah. So this actually doesn't have to do with cosmic rays. It's another thing that I work on. A few years ago, a postdoctoral scientist joined my group, and he had studied magnetic fields on the inside of the sun. And he had a big computer code written long before he was a student that he had been using for this. And at that time, there was a new plasma physics experiment getting started at the University of Wisconsin, plasma in a ball, supposed to study magnetic fields. And he thought that he would apply his computer program to this new experiment. So it seemed like a good idea. But as we stripped out of the code more and more things that have to do with stars and just replaced them with ordinary plasma, the behavior got weirder and weirder. We understood less and less of what this computer code was spitting out.
Interesting.
And we finally realized that there was kind of a contradiction in the basic equations that this program was solving. And we were able to get to the bottom of it. We were able to fix it. And kind of in a triumph of human relations, this young guy was able to go back to his advisor and say, there's this problem, but here's how you fix it. And it all worked.
That is a happy story. And I love that you go back with a solution, not just here's a problem.
Well, that was so satisfying, sealed and delivered.
Absolutely. Well, congratulations to you and your student on this success. And we mentioned some of the different aspects of career in science and some of the things that you have to do. I think it can be hard to find time to read for fun, but that's something that I'm trying to do more of in my life and encourage our listeners to do as well. So I love getting book recommendations from everyone we have on the program. So Ellen, do you have a book that you'd like to recommend for us today, whether it's a science book or a non-science book?
I have read some extremely exciting science books. One of the ones I read most recently is a book called The Glass Universe by Dava Sobel. She also wrote Galileo's Daughter and Longitude. And this is a book about the women who worked at Harvard College Observatory. And basically, kind of from start to finish, did these critical observations of stars and later inferred that stars are mostly made of hydrogen. It's a wonderful portrait of an era, late 19th, early 20th century, kind of how science worked in that time. I thought it would be a big story of sexism. And there's some, but there's just a lot of things really came together for me about how we study stars.
Absolutely. Listeners, I second this recommendation. It was a great book.
You read it too.
Yes, I did. I kind of get into these history of science books. They're a lot of fun.
Yeah, I really like this one.
Very cool. Well, Ellen, we've talked about some different aspects of your career and what you do in your daily life as a scientist. But one thing we haven't really mentioned yet are some of the opportunities that you get to travel. And I think this is a big part of the career of a scientist that I like to highlight to our listeners out there. So is there a favorite place that you've been for science that you want to tell us about today?
Well, been to many places. There's a lot of great science being done all over the world. And maybe the most revelatory place that I went to was the Center for Physics in Trieste that was founded by Abdus Salam. And it's a place that people from developing countries can go and just have a place to work on physics. I went there for a conference a few years ago. It's kind of on a big wooded piece of land outside of town. And I was wandering through one of the paths in the woods. And I heard this distant conversation behind me about string theory. And string theory is one of the most difficult subjects.
Sure.
I think for most people, certainly for me. And these people were kind of gaining on me, two guys. I could hear them getting closer and closer. I thought, my God, what are they talking about? This is so obscure. This is so difficult. This is so hard to follow. Then they passed me, and it was two guys in traditional African garb, brightly colored robes. I'd never seen physicists dressed that way. And I thought, this is so wonderful. It was a great experience. It's always stuck with me.
Yeah, really highlighting that global nature of science. I think that's fantastic. And it's interesting to me that even though you may have nothing in common with someone, the science really brings you together.
Well, it does. And I'll tell you something else. The cafeteria at that center, there's the most wonderful selection of spicy condiments from all over the world.
Ooh. Have you dabbled in those?
No, but I love spicy food. Always squirting hot peppers on my stuff.
Very cool. So you mentioned this was in Trieste. Were you able to explore a little bit while you were there?
I had been to Italy many times, but always sort of Mediterranean Italy. And Trieste is part of Adriatic Italy, and it was part of the Austro-Hungarian Empire. So in some ways, it's very German. It doesn't have the sort of relaxed loveliness that I found in other parts of Italy. But my grandfather was born there. So it kind of meant something to me to see the city and imagine what things were like for him as a young guy. He was born in 1901.
Yeah, it sounds like a wonderful experience then, traveling to this new place, meeting some new people, breaking some of your own preconceived ideas about what physics was like in the world. And we talked about different aspects of scientists, and this is something kind of breaking the stereotypes of scientists is something we love to do on our program, because I think there are so many different portrayals of scientists in the media, in the movies, and I think there are so many different types of scientists and people who don't really fit into those molds. So I like to show this human side of science by really emphasizing the social nature of science and just the fun and funny things that scientists do when they're together. So Ellen, do you have a tradition or a funny story that you want to share with us today?
What kind of story?
Any kind.
Well, I enjoy classical music, and my husband really knows a lot about it. He's a devoted amateur pianist. Mm-hmm. And you go to pretty much any concert and you'll see a lot of astronomers and physicists. For some reason, it's a very common liking among astronomers. I don't know if this makes us seem more approachable or less approachable.
More multifaceted, yeah.
It's also true of heavy metal, but I don't go to heavy metal concerts myself. So my husband is a philosophy professor. And it seems like when philosophers go to conferences, they're very adventurous about where they eat. I hear them talking. They'll say things like, oh, I hear there's this great Polish neighborhood. We can take the train. Or every night they go to a different part of town. Mm-hmm. And astronomers and physicists, seems like we find a place on the first night. And if it doesn't kill us, we go back there the next night and the night after that. And if possible, we order the same thing.
Interesting.
So I don't know.
It's a matter of comfort and convenience, right?
I guess so. Just let's get the food out of the way.
So what's your favorite thing to order when you're out at a conference?
Well, I'm vegetarian, and usually the most reliable place to get healthy vegetarian food is some kind of Asian restaurant. Mm-hmm. I'll seek that out. I said I like spicy food, so if I can find some place that has very spicy food, that's good. Pretty much many kinds of Asian food are my favorite.
Excellent. And one of the things we chatted about was the big questions that you're answering in the lab. And I know you're working on some really great research projects, but usually there's something standing in the way, Ellen, from scientists being able to do exactly what they want and answer all the questions they have in their own minds, whether it's funding or staff or feasibility or limitations in technology. So if I took all of those away, the sky's the limit here. Ellen, what is the one question that you're most interested in answering?
Where magnetic fields came from in the universe. The standard cosmology is that the universe was born in the Big Bang. That's where all the elements, all the atoms ultimately came from. Matter ultimately came from the Big Bang, matter and light. We don't know where magnetic fields came from. Pretty much every star, galaxy, even planet where you could observe a magnetic field, you find one. And we don't know where they came from.
Interesting. So what is the limitation? Or if you could only pick one of the limitations, that's the biggest one, what's keeping you from answering this question?
So one of the most important clues that would point toward a solution to this problem is if the space between the galaxies also had a magnetic field. So there's a super tenuous gas between the galaxies. And if that gas had a magnetic field that just pervaded the entire universe, that would eliminate some theories and favor others. But we know that such a magnetic field must be very, very weak, and there's very little around for it to interact with. So it's very hard to see. Now, recently, There was a wonderful young scientist named Anne Mao who spent 3 years at the University of Wisconsin, supported by the National Radio Astronomy Observatory. And now she's in Germany, but we've continued to work together. And she discovered kind of the most ancient magnetic field known. A magnetic field in a galaxy very far away, so seen a long time ago. And this is a very interesting and important clue also to the origin of magnetic fields. And we need many more.
Interesting. Well, Ellen, in addition to giving our listeners fascinating questions for them to ponder as they go through their day, we love to give our listeners advice that can help them on their own scientific journeys. So, Ellen, do you have a favorite piece of advice that was really helpful to you that you'd like to pass on to them today?
Live your dream. It's still true today, and it was certainly true when I was a kid. Very few women became scientists. So I told you I had a wonderful science teacher in 6th grade. My science teacher in 7th grade was not so wonderful. And in fact, he told me that women could not become astronomers.
Really?
Do not listen to anyone who tells you that. Just learn as much as you can, satisfy your curiosity. Don't expect it to be easy, but don't accept the idea that it's not possible because of who you are.
Absolutely. That is such an important message to give our listeners, Ellen. Is there any other last message you want to give them or a last note of inspiration you'd like to leave them with today?
I don't know. Eat right, get plenty of exercise.
Mm-hmm. Run for good ideas.
Yep. And keep your sense of humor.
Absolutely. This is good life advice, listeners. Well, Ellen, thanks so much for joining us on our program. Can you tell our listeners if they want to learn more about you and what you do, where should they go?
Okay, they should not go to my webpage. My webpage, I think, has a disclaimer that I may look dead, but it just means I'm not updating my webpage.
That's fair.
And I'm not on Facebook. I'm not on social media because they take too much time. But they can just email me. So my last name, Zweibel, lowercase, Z as in zebra, W-E-I, B as in boy, E-L, at astro, that stands for astronomy. Again, lowercase, .wisc, that stands for Wisconsin, .edu.
Well, listeners, definitely reach out, get in touch with Ellen if you have any questions about her work. And Ellen, we appreciate hearing more about you and your stories on our program today. So thank you so much for joining us.
Thank you, Marie. It's been a lot of fun.
It was wonderful to chat with you and great to have you here as well, listeners. We'll see you next time on another episode of People Behind the Science. Your voyage to explore the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to chatting with you next time on People Behind the Science.